Ladies and gentlemen, let's continue with chapter 9 on natural convection. We are making use of the textbook of Cengel and Ghajar. We've done a few sections of it, and I would like to look now at section 9.4, which is specifically looking at natural convection of fin surfaces. This is quite an important application for the cooling of electronic components. In case you didn't know, all your laptops and all computers these days need some extra cooling. It is the challenge that the manufacturers have is to decrease the cost of computers by a factor of 10 and to increase the speed by a factor of 10. The limiting technology at the moment is the heat, to get rid of the heat. So it's very, very important. So with fin surfaces, what we normally have is we've got two flat plates which are at temperatures typically TS and TS, and it will have a certain length L. And this is called the S or the pitch spacing. What happens with these types of natural convection problems is the boundary layer develops, but this one also develops, and then they meet at a stage. It's developing flow, and then it is fully developed from there on forward. In many cases, the designs are actually to optimize your design. You will actually go and determine how long will it take before the flow is fully developed, and then that would be the length that you're going to choose typically in your design. Why? Because the heat transfer coefficients here is very, very high, but from that point onwards, when the flow is fully developed, the heat transfer coefficients are much lower. So with all natural convection problems, what we referred to is for the non-dimensionalized group that is very important is the Grashof number, which is equal to G beta, Ts minus T infinite, so the temperature difference between the plates and the environment, S to the third, and the kinematic viscosity. Now it's very, very important to take note of what we would do here. So this would indicate we are using S as the characteristic length, but then there will be other cases where we will rather use L as the characteristic length. And then there we will of course have L to the third. So you have to be very careful for that. In the textbook there are many, many equations which are given there, and what I always tell you is remember the fine print. The solutions of which equation you should use and how you should use it is in the fine print. So that is the Grashof number. In most cases, we are actually interested in the Rayleigh number, which is equal to the Grashof number multiplied by the Prandtl number. So with many of these equations, they don't give the Grashof number, but they would immediately give the Rayleigh number. So in this case, for example, the Rayleigh number would be equal to G beta Ts minus T infinite, S to the third, divided by the kinematic viscosity. We will indicate in this case that it is based on this distance S, which is the distance from the two plates. And the Rayleigh number would then be equal to the Grashof number, which is this part, multiplied by the Prandtl number. So it's very, very easy. In the textbook, there are again information and equations are given for two categories of problems. Firstly, where the surface temperatures remain constant. And then there's an equation, for example, that would then give the Nusselt number, and the Nusselt number would typically be HS divided by K, C, or just K, multiplied by something to the minus 0.5, And for example, equation 9.31 is one of these examples. So in here, we will most probably be using the Rayleigh number to the S in the calculation of the Nusselt number, and that is then why we have to go and determine the Nusselt number typically as equal to the heat transfer coefficient, and now the characteristic length is equal to S divided by K. Something like that. Sorry, I made an error here. They should be equal to a long equation. So the Nusselt number is equal to HS divided by K, but remember there are just as many problems where they rather use the length L. So you have to be very critical and very careful in these calculations. So the first category of problems or equations in your textbook is for a constant wall temperature, and then the second category is for a constant heat flux. And of course, the specific application that is given to you will determine which category of problem you're going to use in terms of your equations. Let's look at an example. The example is we have a surface with dimensions of W 120 millimeters. We have available in this direction just 24 millimeters, so H is equal to 24 there. And this length, L, is equal to 180 millimeters. And we would like to cool this area. So this area is going to be cooled. This is the available volume that we have. So in this direction, only 24 millimeters. 120 millimeters in that direction, and in that direction 180 millimeters. That is what we have available. So what we're now going to do is we're going to put on fins, and the fin thickness is going to be 1 millimeter, and the environment temperature, T of the environment, is equal to 80 degrees Celsius, and the surface temperature is equal to 80 degrees Celsius. So the question is, go and determine the number of fins that we should put on, and of course determine how far should the fins be apart. So N and S, and then lastly the heat transfer rate. What heat transfer rate would be possible from that set of fins? We are going to work with air as the working fluid. We've got a wall temperature of 80 and an environment temperature of 30. So if we look at the fin temperature, it is equal to 55 degrees Celsius. And if we go and look in table A15, there you'll get the characteristics for air. And then you can determine the K value for the air is equal to 0.02772 watts per meter Kelvin. The kinematic viscosity is equal to 1.847 multiplied by 10 to the minus 5 square meters per second. The Prandtl number is equal to 0.7215, and beta is not given in the table, so we are making the assumption that the air is an ideal gas. So it is 1 divided by the temperature in Kelvin, 273 plus 55, which is equal to 1 divided by 328 per Kelvin. Yep.
So what the 30 degrees Celsius from? Because all temperatures are 80 degrees over there.
You know, by now I'm quite crazy. Yeah, so sorry, this must be 80. So it is a warm summer's day, 30 degrees. The surface is at 80. We need to get rid of the heat transfer. Okay? So, if you go and look at all this reading material available in your textbook, we are going to make the assumption that the temperatures of the fins are going to remain constant. So it is going to remain at 80 degrees Celsius. These lengths are quite short, so it should be a good assumption. But what they also give in the textbook is they actually give the optimum values for S. So that has already been solved. And this optimum has to do with the fact where the two boundary layers meet. Right, and if you go into the textbook, Carl, if you can zoom in there for us at the textbook, there you can see the typical for where we've got a constant wall temperature. There it gives an equation for the optimum S, the optimum spacing, as a function of Rayleigh S, and then also as a function of Rayleigh L. So you can use any one of the two. And then, based on that, the Nusselt number would be equal to 1.307. Okay? So, what we are going to do is, in this case, we do not have S yet. It is what we have to determine. So therefore, we are rather going to use the Rayleigh number based on the length. So the Rayleigh number based on the length is equal to G beta Ts minus T infinite L to the third multiplied by the Prandtl number divided by the kinematic viscosity square. Okay. G is equal to 9.81. Beta is equal to 1 divided by 328. The temperature difference of the surface is 80, minus that of the environment is 30. The length is equal to 0.18 to the third, multiplied by the Prandtl number, and the Prandtl number is equal to 0.7215. Okay. So take note in terms of using this or defining this as an L or an H or a W, I've used the terminology available from the equations. You see that? Obviously, if you're going to define different ones, you need to apply it as prescribed on that, in that sketch. Right, so the Rayleigh number, if you go and work it out, is equal to 1.845 multiplied by 10 to the 7. Okay. And now, if we look on the PowerPoint, we can see that the optimum spacing for the fins is equal to 2.714 multiplied by L divided by the Rayleigh number, and they very specifically say it is based on the length L to the power of 0.25. I'm not going to do the substitution here because there's a Rayleigh number. We've got the length, which is equal to 0.18 meters. The result of that is that we can get the optimum spacing as 7.45 multiplied by 10 to the minus 3 meters. That's not really an engineering answer. That would be equal to 7.45 millimeters. So if the fins are spaced from each other 7.45 millimeters, that would be the optimum spacing for heat transfer. Okay. Now the question was not only to determine S, but to determine the number of fins that we can put onto this surface. So we can say the number of fins is equal to the width that we have divided by S plus L. So if we now would go and put the other fins there, like that. And if we use some color, let's see if that works, then every one of these fins, let's use that as the area of one fin. Okay. Then we've got a spacing of 7.45 millimeters plus 1 millimeter thick. That is the thickness of the fins. So that would be the volume typically of every one of the fins. So that is why I've determined it like this, and the result of that is 12.8 fins. We cannot use 0.8 of a fin, so we are going to use, in this case, no, sorry, I keep on making a mistake. So, sorry, this is 13 point something, one other value larger than 0.5, so we're going to use 14 fins on that surface. And that would give the optimum heat transfer rate that we can get out of that area using the optimum spacing of the number of fins. So if you go onto that area and you put in 28 fins, the heat transfer rate will be lower than this value. So we also have to calculate the heat transfer rate. The heat transfer rate we can get from, firstly, determine the heat transfer coefficient divided by K, and that is equal to 1.307. Okay. Now I don't know if one of you are actually now realizing what we are writing here. A Nusselt number of 1.307, what does it mean? When we spoke about forced convection, what I've said is that if the Nusselt number is equal to 1, then it means that all the heat transfer is by conduction only. If you would take this problem into space, where there's no gravity, so that term is 0, then the heat transfer will only be by conduction. The Nusselt number would be 1. So a Nusselt number of 1.307 means that the fins enhances the heat transfer by about 30%. It is low, but that is typically what happens with natural convection. It has relatively low values of heat transfer coefficients and Nusselt numbers. That is why with many electronic types of applications, they need to use a fan, and these days they are also investigating technologies where they've got so-called microchannels, and in the microchannels there would be a fluid that is actually being boiled and is actually transferring the heat from the material to the fluid. So it is a two-phase process that occurs in those cases. It's of course much more expensive to do it like that, but as I've said, that this is one of the big limitations at the moment for electronic applications, is to get rid of the heat. So if we now do that, we can say this is equal to the heat transfer coefficient multiplied by the optimum spacing, 0.00745, divided by K, which is equal to 0.02772, is equal to 1.307, and the result is a heat transfer coefficient of 4.863 watts per square meter degree Celsius. Okay. I hope somebody realizes that something is wrong. What is wrong? With natural convection, we do not have heat transfer coefficients of order of magnitude of 1,000. It is order of magnitude of 10. So the correct value is actually 4.863. So if you've made this calculation and you would get 4,800, then immediately you should know it cannot be, I've made a mistake somewhere. So there's the heat transfer coefficient. Now we can calculate the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by the surface temperature minus temperature of the environment. The heat transfer coefficient is equal to 4.863. The surface area, we've got 14 fins, but every fin has two areas, because from this area on the right there can be heat transfer, and the area on the left there can also be heat transfer. So there are two heat transfer areas. So it is 14 multiplied by 2 multiplied by the area. The area would be equal to 0.024, 24 millimeters, multiplied by the length, which is 0.19, 180, sorry, 0.18, and the result is a heat transfer rate of 29.4 watts. So typical heat transfer rates of these types of equipment is 60 watts, 100 watt, something like that, relatively small values. Any questions? Yep.
For your number of fins, which values did you use?
Sorry, the number of?
The fins, which values?
Fins, yes.
You used your width of 120 millimeters and your S of 7.45 millimeters,
Yep.
and your L, is there not 6BT of 1?
Now the number of fins is determined by that area, 120. Okay, so it is 120 multiplied by the volume of each fin and its spacing. Okay?
The value, why do you use that? When you use that, then L, you don't get that value.
Sorry, I cannot hear. Wait.
Value of L in the denominator.
Yes.
You use that value, you don't get
Okay, do you mean sorry, I see what you mean. It should be S plus T, the fin thickness. Okay? If all have it, I've made an error here. So the number of fins would be determined by this length and the number that we can get in. So with each one of them, it's the spacing plus the thickness of itself of the fin of 1 millimeter. Great, okay, thanks. Right, the next part of the work in chapter 9 is on inside enclosures. Inside enclosures. And one of the best examples of that is glass. So if you've got two glass plates, and this is maybe on the inside of a house, it is hot, and there you've got the outside of the house, which is cold. Right, so if we've got the hot part and the cold part, and you took it up into space so that there can be no natural convection, then just as an example, the heat transfer rate would be approximately 10 watts. And this 10 watts can be 10 watts per square millimeter or per square meter or whatever. So it means that this heat transfer rate is by pure conduction only. However, in the real world, what is going to happen is that this part is heated, so the air next to it will rise. There it will do something like that, so it forms a recirculation area on the inside of these two glass panels. The result would be that the heat transfer rate would increase typically by a factor of 3, just because of these these currents. We don't really have this problem that much in South Africa, but in many other countries where they've got quite extreme weathers, where on the inside they want a temperature of 18 to 20 degrees, and outside it is 0 or minus 10 or minus 20. And in almost all those types of houses, they use these two plates, and then this area is full of air or it is evacuated. Excuse me. Okay, another application would be to have the two glass plates like this. And again, this one can now be heated, and that one can be the colder one, or you can do it the other way around. This one can be the cold one, and that one can be the hot one. And with all of them, there are different equations available in the textbook. With all of them, it's about getting the Rayleigh number. Then you calculate the Grashof number, because with all of them, fundamentally, we've said that the Nusselt number is equal to a function of the Reynolds number, the Prandtl number, and the Grashof number. Okay. Now with forced convection, this term is quite large. But with these types of problems in chapter 9, in most cases we ignore the Reynolds number. The velocities are very, very low. So therefore you need to get a correlation of the Nusselt number as a function of Prandtl-Grashof number, or then as a function of Rayleigh number. And many, many examples are given there in your textbook. Now just to give you an idea, what would you consider as one of the best insulation materials? You all know there's insulation materials like polystyrene, which can be used in your roof, or in some cases between the two, when they build a house, not really in South Africa, but between the two walls there can be an air cavity, or they can put polystyrene in it. But one of the best materials that you can use, as you wouldn't believe it, is air. So air actually has a very low thermal conductivity value. Typically we have seen just now with an example 0.2772 watts per meter Kelvin. Now in table A6 in your textbook, there's a table that gives all the K values for different materials. If you would like to look at that quickly, I'm going to give you a second. Okay. So that is on page 914 in your textbook. About 40 or 50 types of materials are given there, as that falls into the category of insulation materials. So if you go and look at different insulation materials, cork is being used as an insulation material. Now cork has a value of 0.039 watts per meter Kelvin. So air is a better insulator than cork. If you now go and look at things like cellular glass, then the value would be equal to 0.058. If you would go to mineral wool, then it would be 0.046. Polystyrene, value would be 0.023. 0.023, it's still higher than that of air. However, if you really want to get low values of K, you need to evacuate this air out of that cavity. So you need to evacuate it. So just to give you an idea, when you start evacuating it, then the thermal conductivity would drop to 0.00016. So there, for the first time, you've got a material with a K value lower than that of air. in our laboratory, we do lots of heat transfer experiments. I don't know if you've seen this type of material. We call it Armorflex. Okay. And we typically use this as a material on surfaces which are being heated to about 60, 70 degrees Celsius in an environment of 20. Now we need to put on about 300 millimeters thick of this on the tube so that we can decrease the losses to the environment to about less than 1%, just to give you an idea. So in the thermal Armorflex has a K value of 0.036. Okay. So again, if we now compare that to that, then I think the question that you can ask is, but why do you use Armorflex? Why don't you use air? Okay. These values of air would be when the air is stationary. It is not moving. So that will work in an environment where G is equal to 0. But because of the natural convection, this value for the K will be much higher, maybe 3 times higher or something like that. So that's why we use the insulation material. Okay? And with the insulation material, the thickness of the insulation is so thick that this side of the insulation material is about the same as that of the room temperature. And then you do not have any more really heat transfer to the air. Okay. So do not underestimate air as an insulation material. Fortunately, we are very fortunate that K has such a low thermal conductivity, therefore air. Otherwise, if there was a fire here, you would burn yourself. The air is a natural insulation material between you and the fire. And the result of that would be that the only heat transfer that you're going to get in most cases are the radiation heat transfer. It is not going to be the conduction or the convection. Another example. This example, we've got now glass. And we've got air inside the glass. This distance is 20 millimeters. It's a typical distance that you would get. That distance is equal to 800 millimeters. And the distance in that direction is 1,600 millimeters, 1.6 meters. And this part of the glass is at 12 degrees Celsius. It is not a very high temperature. I mean, if that's your room temperature, then in most cases you will probably be cold. And let's suppose on the outside the temperature is about 2 degrees Celsius, a typical winter's day in South Africa. The question is, determine the heat transfer rate for this example. Again, we need to get the fin temperature, which is 12 plus 2 divided by 2, so that is 7 degrees Celsius. Again, we go to table A15 to get all the properties, and the properties are K is equal to 0.02416 watts per meter Kelvin. The Prandtl number is equal to 0.7344. The kinematic viscosity is equal to 1.4 multiplied by 10 to the minus 5. And beta is, of course, 1 divided by 273 plus 12, and that is 280. 1 divided by 280. So if we look at the textbook quickly, then you'll be able to see that there are equations for all the different orientations, for the two plates in a horizontal position, at an inclination angle, in a vertical position, and here are typically what we are interested in. So there you can see the Nusselt number, you can see the calculation of the Grashof number, on what it should be based, etc. So all the information is there in the fine print. Now I want to make sure that I do not run out of time, so I'm going to skip a few things. So we're going to calculate the Rayleigh number, and we're going to base it on the length, because that is what they tell us. If we calculate the Rayleigh number, it is equal to 0.05 multiplied by 10 to the minus 4. You can go, when you're at your house, you can go and do all the substitutions and check it. Then, what is also relevant is that they want the aspect ratio of this case, and that is equal to 800 divided by 20, and that is equal to 40. And then you're going to use equation 954 that gives the Nusselt number is equal to 0.42, Rayleigh based on the length to a quarter, Prandtl to the 0.012 multiplied by the aspect ratio, H divided by L, to the minus 0.3. Here you can see the Rayleigh number based on the length. So there we've calculated it, we've used the length. So there will of course be a Prandtl number there. We're going to put it there in there, and then we're going to calculate the the Nusselt number, which is going to be equal to 1.4. If it's lower than 1, then you must know you've made an error. Nusselt number of 1.4 means the heat transfer will be enhanced by 40%. It will be 40% higher than that of conduction. Then we can say the Nusselt number is equal to H, L divided by K is equal to 1.4. Why do we use L? Because they give us the equation like that in the textbook. They base the Nusselt number on the length L. And you can go and calculate the heat transfer rate as equal to 0.02416 watts per meter Kelvin. And then you can go and calculate the heat transfer rate, which is equal to 27.1 watts. So please go and do it at home. So glass excuse me, is a very important application in air conditioning and refrigeration companies, because glass is where most of the heat losses occur. In any house or any building is through the glass. And there has been many, many sophisticated glasses that has been developed which have better properties and poorer properties, but there are some information in your textbook on that. Again, it is not all the information that you need, but it is enough information just to help you in the right direction, so that you can make use of manuals like, for example, the ASHRAE manual or the Carrier manual, which have much more tables and detail, and from there you can get the heat transfer characteristics much more accurate, and or from the manufacturers of the glass. Right. Now the last part of this chapter that I want to do is combined forced convection plus natural convection. Remember, FC is forced convection, NC is natural convection. So there are applications where if this is a plate and you're going to get the natural convection in that direction, so that is hot. Now what you can do is you can also use a fan there. So now you've got natural convection plus the forced convection. Okay. We call this assisting flow, because the two are helping each other. They work in the same direction. But then you can have an application where this wall is being cooled Okay. Then the natural convection will occur in that direction. If you now add a fan here, then this will work in the opposite direction. So this we call opposite flow. Opposite flow. And then the last type of flow is where we've got maybe a heated cylinder and forced convection there from the side, and the results of that would be the natural convection doing something like that. And this is called transverse flow. Transverse flow. How do we handle problems like this? Well, it is actually very simple. We do it by calculating the effective Nusselt number by considering getting the heat transfer from the forced convection only, the forced convection, so it is just flow over a flat plate, and then we add it to that of the natural convection. And typically we do it with an equation like this. It's Nusselt number to the n plus or minus Nusselt number to the n, and this is natural convection and that is forced convection. So this Nusselt number is, we call that the combined Nusselt number. The combined Nusselt number is the Nusselt number of forced convection plus natural convection, but I think I've made a mistake here. I think it must be 1, it's multiplied by 1 to the n, something like that. The equation is in your textbook. What is important to understand is that this plus or minus is for your discretion. So you have to figure out, do I plus it or do I minus it? And that is actually very easy. So if they're working in the same direction, then the heat transfer would be improved. So therefore, I would use a plus sign for there. Okay? If it is in the opposite direction, you would use a negative sign there. Okay. And if it's in the transverse direction, then they help each other, it's a plus. Okay. So just to repeat, let's suppose you get a problem like this in the exam or the test. Here's the fan, forced convection, and there's natural convection. So natural convection and forced convection. Then you're first going to look at the plate and you're going to get the natural convection Nusselt number first. And it's going to be a function of Grashof number, etc. So you're going to calculate it. Let's suppose it is equal to 5, which would be a very high value. Okay? And then you would ignore that part and you would say, well, this is a flat plate and I've got a fan and the flow is over the fan. So I would consider this as forced convection only. And I will go and calculate the Nusselt number. It will be a function of Reynolds number. You've done it already in chapter 5 or something like that. Okay. Now let's suppose this value is equal to 10. Then it's very easy to say the Nusselt number combined would be equal to the value of 5 to the n plus the value of 10 to the n to 1 divided by n, and the value of n is normally approximately a third or a quarter, 1 divided by 3 or 1 divided by 4, something like that. And then from that you can get the effective heat transfer coefficient, which will be higher than this heat transfer coefficient, and it will be higher than this heat transfer coefficient. And from that, you can calculate the heat transfer rate. Okay. Any questions? Okay, if not, all right. Okay, so ladies and gentlemen, in terms of the test coming up, the test goes over chapters 7 to 9. So chapters 7, 8, and 9. Okay. And there will be three questions one question on each one of them, and then there's another question from Dr. Leroux about radiation or something like that. Can't remember. Okay. Now, would you like a tip? Okay, Carl, you can stop, sorry.